Let me start recording. Okay, maybe let's get started. Okay, so let me first briefly introduce our speaker today, Shuyang Ling. He's a professor from Shanghai, NYU Shanghai, and his research interests include machine learning, optimization, and computer sensing, inverse probability imaging, and today he's going to talk about neural collapse phenomena. And I'm not going to read the title. So Shuyang, please go ahead.
Okay, thanks, Bing, for the invitation and the introduction. Also, thanks for organizing this online seminar. Actually, has been subscribing for a long time. Today I will talk about some of my recent work with my student Wanli Hong. He is a PhD student at NYU Center for Data Science, and also actually my student. And we have been working on the neural collapse phenomenon since last May. And I will talk about some of the work we have finished last year, and also some ongoing work we probably will be able to post in the archive next month. So it's about the neural collapse phenomenon for the unbalanced data set. Okay, so let me first give an outline of my today's talk. Just in case some of the audience don't know much about neural collapse, I will briefly give a brief introduction to it. Then I'll talk about the mathematical theory behind it. And a very famous model for it is called the unconstrained feature models, or also known as layer paired model. And in particular, we'll focus on the imbalanced data set and also the so-called minority collapse. And also we extend these neural collapse phenomena to shallow neural network, especially the two-layer neural network. And we have some ongoing work, and we can briefly mention it. Okay, so let's start with a deep neural network like ABC. So we consider a neural network of the following form. So it's f of x is equal to some linear classifier W transpose applied to h of theta. So here I always mention the feature vector h of theta, and the weight is a linear classifier. And the neural network is basically this type of architecture as a highly nonlinear functions with some activation function, let's say sigma. It could be Raru, it could be different sigmoid, different type of activation function. Okay, so when do the training, usually you get the data, and let's say xi and the yi, then we just minimize the empirical risk over the parameter theta. So the theta is essentially the weight of each layer and also the bias. And here in particular for the classification problem, we use a cross-entropy function. So it's quite standard in the practice. And here, yi, because it's a label, for example, it's a K-class classification, so yi would be basically the one hot vector. Okay, so the interesting things about this training process. So deep learning overall, it's a great success as a technology, but in terms of the theory, it's still quite limited. So in 2019, a group of people from Stanford, including Papyan, Han, and Donoho, they observed in the training of the neural network that there's certain type of implicit bias. It's called a neural collapse. So let me try to briefly mention what does it mean. So there's a two type of simply speaking, there's a two type of collapse. The first is called a variability collapse. So which says that, let's say if you have k classes of data, and each class contains same amount of number of points, let's say n points, let's say x ki, k stands for the class number, and I stands for the numbering of the data in each class. So it says that if the neural network is large enough, then if we train the neural network long enough, then the feature of each point, let's say xki, hxki would actually collapse to the mean vector of that class. So which means each ki, hki will converge to the mean. And moreover, also the mean vector, mean feature vector hk bar also exhibits a certain type of geometric structure. So in particular, it says that the pairwise angle between the hk bar would actually be the same. So essentially, the mean feature vector would converge to the so-called regular simplex or simplex ETF. So I just stole this picture from Donoho's paper is basically says the following. So if we look at the mean feature vector, let's say H bar is actually consists of k vectors, and each of the vectors actually the mean feature of each class. Then it says that if we compute the pairwise angle and also the linear classifier, it will actually becomes a projection matrix. So I means the identity matrix, JK would be the constant matrix. So it's essentially the simplex, like a regular simplex in k-dimensional space. Okay, so here there's an illustration. So you can see the red dot is actually the weight of linear classifier, and when the training process going for evolves, the linear classifier actually would exhibit this equal angular tight structure, and the blue curve, the blue vector would be the mean feature, and the green dot would be the ETF simplex, and also this dot would be the feature vector of each training data point. So this is actually some certain type of structure that observed in the training of the neural network, and it's interesting because it seems to be the training process. The feature won't converge to arbitrary vector. It will actually has exhibit this type of interesting structure. So that's why we are interested in understand from the theory side that why this happens, why this neuron collapse phenomenon happen. So one of the big challenges of understanding this neuron collapse phenomenon is the nonlinearity of the deep neural network. So which means that when we try to train a neural network, the objective function could be highly non-convex. So how to deal with it? And we need a certain type of simplification. And one of the way of doing the simplification is to use the idea from the approximation theory. It says that if we have let's say a continuous functions on a complex set, then we can always construct even a shallow neural network can arbitrarily approximate the neural network. Okay, so which means a neural network can approximate anything, or if we given finite many points, it actually can interpolate anything. So in other words, the expressiveness of this feature vector could be extremely powerful. So that's why one way to do the approximation is to approximate, to replace this constraint, this feature vector, which is actually the range of the neural network by arbitrary vector, let's say HKI. Okay, so that's called an unconstrained feature model. So it's actually proposed by a group of colleagues. Tong Van is actually at Peking U, and these people's colleagues actually proposed this model, and it's basically that we can replace this h of theta by arbitrary vector and try to understand these objective functions instead and see whether the collapse phenomenon would occur. But of course, there's some issue about it. So the advantage of doing it is that it's simplified the model dramatically. But on the other hand, it's also basically because it's replaced by arbitrary vector, so which means this vector actually has nothing to do with input. Okay, so we don't see the link between the input and the output. But on the good side, it still can explain something because of the approximation theory. Okay, so based on this model, actually there's a lot of work in the past few years, especially on a balanced data set, which means each class has same amount of points. And then among this work, people can show that, let's say on the unconstrained feature model, this simplex configuration, which means the mean feature vector that it exhibits, this equal angular tight frame would occur. Okay, and there's a long list of work on the different type loss function, let's say the cross-entropy loss and also the mean square loss. And also there's some of the work that are beyond the unconstrained feature model by considering adding a bit of nonlinearity to it. But still, all this type of model would assume the data set are balanced. And also the model actually decouple the input data, which by assuming it's unconstrained feature. And our focus, the first work focus will be on the imbalanced data set, which means in each class, the points, the number of points, training points won't be the same. And in this case, in fact, this type of a scenario would actually occur in many of the scenario cases. For example, in medical data, usually the number of samples for healthy people are much larger than the unhealthy or the patients. So which means if we feed these data to a model, probably the model would favor the majority class and ignore the minority class. So that's why we want to see how the neuron collapse phenomenon would occur, especially in the imbalanced data set. So in particular, we'll focus on the following few questions. The first question that suppose the neural network is over-parameterized, whether the collapse will occur, either theoretically or empirically. And the second question is that whether the mean feature vector would still form an equiangular frame, which means the simplex, regular simplex. If not, how and what type of phenomenon would observe for the mean feature vector? And regarding the imbalanced dataset, there's some work already. For example, the work by Fan and also Wei Jie, they actually discuss a minority collapse, which means that the model would favor the majority and it completely ignore the minority. And also there's some work study the neuron collapse for imbalanced dataset on the mean square loss. Okay, so first let's do some show some numerical experiment to see whether the collapse phenomenon would occur for the imbalanced dataset. So here we try the two type of dataset, CFAR10 and FMNIST, and we choose three different type of neural network, the retinal VG11, VG13, and also we assume the dataset are imbalanced. So here we choose two different type of settings. The first type of settings that in total we choose 10 classes. Okay, so in these 10 classes, there are 4 classes equal to, let's say, consists of 5,000 points, and 3 classes consist of 4,000, etc. And the second case is the same. So which means here there's several classes share the same amount of points, but among different type of classes, the number of points would be different. And we want to see whether the neuron collapse phenomenons would occur in this case, and if we train the neural network long enough. So here we use these empirical risk minimizations and also use the activation regularization, which means we add the regularization part on the feature vector, and also we choose a set of regularization parameter and using SGD with certain type of diminishing step size and see whether the collapse will occur. And to measure the collapse, we actually define these covariance matrix. So we define two types of covariance. The first one, sigma W, it's actually a way to measure the weighted covariance, okay, within the classes and between classes weighted by the number of points. And the second part is sigma B. Sigma B is actually covariance matrix of the mean feature vector. And we can see if the sigma W is close to 0, then it's possible that each HKI would actually be very close to its center mean. So the neuron collapse would occur. Otherwise, it probably won't occur. And our numerical experiment show the following. So if we take the trace of these sigma W, also basically divide by the reweighted by the between class the mean feature vector covariance, we see the following. So here's epoch. We run 1,000 epoch, and we see that if we run if the epoch is long, the training time is long enough, we see that the trace actually look very close to 0. It's almost 10 to the power negative 10. Except only one case, the VG11 converts to about 10 to the power negative 6, but still it's quite small. So which means that even if for these two different type of setting, it's both unbalanced, the neuron collapse actually occur. So which means the feature vector of the same class would actually collapse to one vector. Okay, so then the question becomes how to understand it. Why these neuron collapse will occur for the unconstrained feature for these over-parameterized neural network. So to understand it from the theoretical perspective, we still consider the unconstrained feature model by replace the feature vector by arbitrary vector. Then we try to minimize this function. So it's a function over the weight, linear classifier, the feature vector, and also the bias. Okay, and in fact, the nice things about it is that, in fact, this model, we can rewrite it and it becomes a convex function if we consider unconstrained feature model. For example, if we, let's say, fix this product form, the W times H, W transport times H, and then minimize the regularization term, actually you would observe that this actually becomes the nuclear norm of the product matrix Z. So nuclear norm here means the sum of singular values. Okay, so in other words, if it's over parameterized, which means H as a dimension is very large, then this program is actually equivalent to this program. Okay, so we let Z to be this K times N matrix, and then minimize it. Then it suffices just to minimize over the Z component instead of separately. Okay, and then remember, because the cross-entropy is convex functions and also affine, and here's a convex penalty function. So we just basically need to understand what type of behavior this solution would get. And here, it's in fact, it suffices to consider this Z. We usually call it a prediction matrix because it's equal to the linear classifier applied to the feature matrix. Okay, that's because if we observe this Z as a global minimizer to this program, we can basically do SVD. Then we get the global minimizer to the original unfactorized form, W times H. Okay, so now basically we need to understand what type of solution look like for this program. Okay, so in fact here is our first result. So we show that under the unconstrained feature model, even if the points are, even if the data set is unbalanced, which means in each class sample size are different, still we would have the within class collapse. So which means the prediction vector, and also it means the mean feature vector, the feature vector would collapse to its mean. So each zki would equal to its mean, zk bar. Moreover, it's centered. Okay, so it's a which means on the unconstrained feature model, indeed, the neuron collapse, the within class collapse would occur. Okay, so the second question would be whether the mean feature vector would occur. What type of mean feature vector property we can have? Because in the balanced case, this zk bar would actually have this equal angular structure. But what happened to the unbalanced case? Okay, so in order to make our description precise, we need to define a bit more notation, but it's actually quite straightforward. So let's say you have k classes, and the class the data size is ordered in a descending way, and so the gamma j is equal to the number point, the order index that equal to nj. Okay, so in fact, this is basically we categorize the classes based on the sample size. Okay, so each gamma j consists of all the classes index that they share the same data size, and then what our results show the following. So instead the mean feature vector or the mean prediction vector Z bar would have this equal angular type frame. It would actually exhibit this block structure. So what does it mean? It means that the mean prediction vector Z bar would actually equal to this summation of this rank 1 indicator vector. So so this indicator vector is essentially the vector that it's either in 1 or 0, and gamma here stands for these. Usually, it's used is represent this gamma j, represent the index of the same class, the classes that share the same data size. Okay, and also the bias vector also have this property. Okay, and so which means in the unbalanced case, this mean feature vector won't be equal angular tight frame again, but still it would have the block structure. Okay, so we can actually try to justify it from the numerical experiment. So here we basically still use the data set from our previous experiment, and then we basically run the experiment and then compute the mean feature vector after 1,000 epochs. And here, each column actually represent one of the vectors zk. Okay, each column here, and we can see that. So here, because for both two settings, there are 3 different type of giant classes, and in each giant classes there are 3 different classes, right? Each classes with a constant same amount of points, and we see that within each block, okay, the block is actually constant. Okay, so across all the examples, so in other words, so our result actually to some theoretical result to some extent reflect the reality in the empirical simulation. Okay, and also we can see what happens, how the feature vector would have compare with how the prediction vector would compare with the solutions solved by the convex optimization. So we see that if we do this simulation, we show that the empirical prediction vector would actually match, especially for the feature vector, it would actually match the solution solved from the convex optimization. The error is almost about 1% to 5%. Okay, but for our case, the bias does not fit well. But for the prediction vector z, it's actually a good approximation. So which means that to some extent, the empirical and the theory matches well. Okay, so also our result would cover the balanced data set as a special case. So for the balanced case, which means n1 all the way to nk are the same. It's equal to the capital N divided by k. So capital N is the total number of samples, and the k is number of classes. And then we can show that the prediction vectors, mean prediction vector matrix, the z bar, would actually become this identity matrix minus the jk constant matrix. So it's actually a centering matrix, and the bias becomes 0. But here, the z would the constant a would depends on the choice of the regularization, because we know that the lambda z is essentially the coefficient in front of a nuclear norm minimization. So if it's too large, it actually with a threshold, all the singular value becomes 0. So that's why we have 2 regimes. If the lambda z is too large, which means we penalize too much on the singular values, it will become 0. Otherwise, we actually have a that depends on lambda z. So lambda z would be the nuclear norm, the coefficient in front of nuclear norm minimization. Okay, and in fact, the proof idea is quite straightforward, and basically we leverage the data symmetry and also the convexity of the objective functions, and then we can show this block structure of the mean feature vector, and also these are for both the unbalanced case and the balanced case. And moreover, it actually can be applied to different type of setting, even if we have some different type of constraint. That's actually the part I can discuss later on. Okay, so that's the first thing we actually answer is about what type of to summarize what we have done so far is that we show that on the unconstrained feature model for the cross-entropy loss function, in fact, we have this norm collapse phenomenon, which means the mean feature would converge to the the feature would converge to mean feature, and also mean feature would exhibit this block structure, but it's no longer equal angular tight frame. It depends on the data size. And the second things we want to talk about is about the minority collapse. Is about if let's say you have one class is very large, one class is very small, what type of a solution you would get? What type of output of the training would look like? So let's try to make it more precise by considering a special case, but this special case is actually quite illuminating. So let's think about there's two giant classes, A and B, and in each cluster, A or B, it contains, let's say, Ka of different classes, and each distinct classes will contain Na points. Okay, so in total, the number of samples would be equal to Ka times Na plus Kb times Nb. Okay, then we want to see what type of what the mean prediction matrix would look like, and how it depends on this parameter. Let's say Na, Nb, Ka, Kb. So still we'll look at this objective function. Okay, but remember there's only two giant classes, and from the previous theory we know that in fact this mean prediction matrix will actually have this block structure. So on the off-block diagonal part would actually have becomes constant, and on the diagonal part would have a centering matrix plus the identity. So because we need to make sure that each column is actually centered, and also it has these two block by block structure. Okay, but we don't know in fact what these parameter A, B, C, D are how they look like. Okay, and in the earlier work, they find a quite interesting phenomenon called a minority collapse, which says the following: is if the imbalance ratio, which is defined by the Na divided by Nb. So here we assume, let's say that Na is much larger than Nb, or so it's measured by this ratio R, and then it says that if the ratio R is much larger, getting larger and larger, the prediction on the minority class, which means the cluster B, will actually becomes negligible. And we want to see how the minority collapse will depends on this imbalance ratio, which means at a certain level, let's say if R is equal to 100 or 50, whether the minority collapse will occur. So we want to understand this. Okay, so in fact, these questions actually can be answered just basically considering the unconstrained feature model. So we show the following. So it all depends on this parameter lambda z. Okay, this lambda z is actually the regularization parameter in front of the nuclear norm. So it says the following. So let's say Na is bigger than Nb. Then if lambda z is small, which means it's smaller than square root of Nb divided by the total number of the samples, and then we can show the mean prediction matrix Z bar is actually unique. Moreover, all the coefficient A, B, C, D from the previous slides here are actually positive. Okay. And then if we increase lambda Z a bit, let's say if the lambda Z is slightly bigger than this plus an epsilon, and then we can show that the mean feature matrix have this structure. So you can see the highlighted part is actually on the left column, on the right columns. So we can see the right columns, it actually becomes a rank 1 matrix because it's the J is actually the constant matrix. So it actually becomes each vector, each column would be the same vector. So in other words, as long as it's bigger than the lambda Z is slightly larger, then the prediction on the minority group actually becomes constant vector across all the classes in the minority group. And if we increase a bit more, let's say if it's slightly smaller than square root of Na divided by capital N, then the left columns would be, the right columns actually become 0. Okay, and in particular, if it's between these two different regimes, it's square root of Nb divided by N plus epsilon and the square root of Na divided by N minus epsilon, so the structure of this lambda, this z bar would be either of these cases. But in fact, we are not able to show this monotonicity. We only can show this there exists lambda star for the bias-free case. Okay, and for the last case would be if lambda z is large enough, it actually becomes 0. So all of these structures actually precise to some extent that it's sharp in theory. And then the natural question here would be how this would related to this to the reality. And we show so we present some, we can present some numerical here. So still we choose two data sets, and we choose there's 5 classes. Each class consists of 500 points, and 5 classes consists of 100 points. And then we train the neural network, and then we try to see how the z bar would depend on this regularization parameter. And we show that so here first we have this 2 threshold computed here, and then we show that on the different level of lambda z, okay, this plot actually changes. And in particular, if the lambda z is approximately equal to the first threshold, 0.0033, you can see on the right block, it's actually becomes constant. So which means that the minority collapse actually occur in this case if lambda z is choosing to be slightly too large. And also we show that if the threshold is a bit too large, which means it's if it, let's say here for this experiment it would be 0.0063, also we would actually have the complete collapse. But it's actually smaller than our theoretical prediction. We don't know exactly why it happens, but it's possibly due to the error actually error incurred from the experiment. But the interesting thing that for the minority collapse, it actually give a quite nice prediction here for the first for the minority group actually vanish. And the second experiment we show is actually the limiting case. Is a scenario when let's say you have R is equal to NA divided by NB, the imbalance ratio goes to infinity. What type of things it would happen, and also we want to see what happens if R is fixed. Let's say the imbalance ratio is fixed, and then what happens if the sample size goes to infinity? What type of phenomena? Whether neuron collapse occur? Whether what type of structure the mean feature vector would have? And here's our result. It shows the following. It shows that, let's say, if R is greater than 1, so which means the unbalanced always assumes the A class is actually the majority class, and then we show that if the ratio R is greater than some threshold, okay, and then the neuron collapse, the minority collapse occur. Okay, so in this case, essentially we said that we actually fix the lambda z, but we let the imbalance ratio change. But in fact, the proof is just a direct consequence from our previous theory. So it says that if R is larger than this a very precise number, the minority group would collapse to a single vector. So this actually also can be shown from the experiment. We show that let's say, so in this case, threshold actually computed explicitly, the threshold is 300. And we see that if the imbalance ratio R is greater than, let's say, 300 as a threshold, the prediction on the minority group actually becomes constant. So it's a precise characterization of when the minority group, minority collapse occur. Okay. Okay, so the second case is when what happens if R goes to R remains constant, which means the imbalance ratio is constant, but the data size goes to infinity. And this is quite an interesting case because we know that given a fixed R and a fixed N, the the feature vector, mean feature vector, won't be like pairwise share the same angle. But what if the sample size is large enough? So which means that we set R to be fixed. It's constant, but n goes to infinity. And here's what our result. It shows that the parameter we have discussed before, the ABCD constant, will all go to 1. So which means all the parameter n, an, bn, cn, dn, they all goes to infinity at the same rate. And what does that mean? It means that the effective imbalance actually diminishes if the sample size is large enough. So which means even if the data set is unbalanced, but if the sample size is large enough, which means n goes to infinity, then the mean feature vector will still becomes equal angular tight frame. And this actually can be reflected from our experiment, which show in this plot. So here we let NA to be NB is NA divided by NB, the imbalance ratio is equal to 2. And then we increase the number of sample size, NA from 500 to 5,500. And then we compute the pairwise angle within the class A, class B, and also between the class A and B. And we show the following. So if we compute the mean angle of all these 3 objects, we show that all of these angles, the dash line, all goes to the equal angular angle. So which means it's about, the cosine angle is about -1/9. So the short story here would be, even if it's imbalanced, but if the sample size is large enough, it will actually the effect of these of the imbalanced data set would actually the imbalance effect would actually becomes negligible. Okay. Okay. So that's actually the first part of the talk. And so then I would basically spend about 5 to 10 minutes to talk about some of our ongoing work. It's about beyond the unconstrained feature model. So because the unconstrained feature model, we find the weakness is that it actually decouples the data point and also the output by replacing the feature by arbitrary vector. So here, in order to understand what happens if the features are constrained on a neural network, we consider a very simple model, the 2-layer neural network, which means with the Raru activation function. So W1 would be the weight in the first layer, and the W2 would be the linear classifier. Okay, so X is the input. And still, we consider this training process, but here we consider a particular type of regularization, the activation regularization, as which is consistent with our discussion before. And we want to see when this neuron collapse happens for this 2-layer neural network, which means the data is actually dependent, the features actually depend on the data. Okay, so first we probably need to understand, so first this objective actually highly non-convex. Okay, so first thing we want to understand is that suppose the dimension is large enough, which means W1, the dimension is large. What would be the global minimizer look like in this case? Okay, so it's actually different from the previous case because here the feature is actually positive, so because it goes through this Raru activation function. So it's actually called a positive feature. And we want to first see what the global minimizer look like. And in fact, this answer can be simply understood by basically do some relaxation. So the relaxation is basically still relax this to the unconstrained feature model. But finally, we will go back to the constrained model. So here, if we let this H to be this feature, but here we just basically assume it's non-negative. So it could be arbitrary matrix. Then we actually have this unconstrained positive feature model by assuming W and H are arbitrary, but also we require H to be positive. Okay, and the Y here would be the label vector. So here we consider a special case that the class is actually balanced for simplicity. And we want to understand that what a global minimizer look like in this case. And the difficulty of solving these programs is because here you have this non-negativity constraint. And in fact, it's not simple to reduce this to a convex function directly. But still, we can do it by a relaxation. So here, in fact, if we let Z to be this product matrix, U to be this W transpose times W, V to be the H times H transpose, this feature vector, it's basically some type of lifting. Then we can show that this program, a convex relaxation of this program can be written down as this program. But here, the V will be positive. It's a non-negative matrix. And this program, actually, we can solve that exactly. And we can see that for the global minimizer, this V would still would be equal to this Y times Y transpose. So the A would be a complicated expression, but the simple story would be the feature vector would still have the collapse for this unconstrained positive feature model. So it's proportional to Y. Remember, Y is actually the label vector, so it's either 0 or 1, and H bar would be equal to identity. So which means the mean feature would be orthogonal basis, and W transpose will still be the centering matrix. And the same result actually obtained in a very recent work by Dan and Tran in the January in 2024. But here we can use a different approach to show this. And one of the biggest difference of this positive feature model with the unconstrained feature model is that here the feature will be orthogonal basis instead of a centered vector. But still it can be done using convex relaxation. Okay, then we go back to the constrained model, the nonlinear model. Okay, so which means that we're going back to this two-layer neural network, the review activation function, and we want to see when the neural collapse would happen. So in fact, this problem can be justified by reducing this problem to a feasibility problem. So in fact, it says the following. So if we want to show, let's say, given a data set x1 to xk, and we want to ask whether neuron collapse would happen, it's actually suffice to ask whether, given this data set x, we can always find a weight vector, let's say wk, and you apply this to the data matrix, which means each data point of dimension d, make inner product with wk, it will become this one hot vector. Okay, so the core question would be this: can we find out w1 to wk? So each wk would correspond to one class, so that so this data set xk transpose applied to wk would becomes constant, and then this wk applied to the rest of the points of the different classes would be negative, because if it's negative, then if we apply the rule activation function would become 0, and if we apply to this one, it would stay the same. So which means if we can find this wk, then it means that we can always find out a weight matrix, let's say w1, w2, so that the solution would becomes this orthogonal, the feature would become this orthogonal basis. So the question here becomes whether we can find out a wk for this case. It means for the same class, xk would be 1, the rest of them will be negative. So it's actually some type of separation, right? For the case class, you can find a hyperplane so that they're always on the same hyperplane, and for the rest of the points, it would be below on the one side of. For the rest of the points, it would be on the other side of the hyperplane. And in fact, in generally, to solve this problem, it's not difficult, because we can just using some linear algebra knowledge, we can do it. For example, if X is a full column rank, let's say if D is greater than K times N, which means if the dimension of the data set is large enough compared with the data size, then using linear algebra, we can always construct such a WK, just basically by solving a linear system, okay? So that's not surprising. So which means if the data dimension large enough, and it's also larger than the data size, then we can always find out a vector make the collapse happen. And also we can have a negative result. So if the dimension is too small, so which means the data dimension is much smaller than the sample, then we cannot make this linear equation have a solution. So in this case, the collapse of course won't happen. Okay, so then the question becomes, what happens if D is between these two numbers, right? N and K times N. Okay, so here I will just give a simple result, a simple case. But of course, the result here I present, we can extend it to a more general case. So let's say if D, if the data dimensions become over between N and K times N, and also we only consider two classes. Okay, so it's basically a Gaussian mixture model. So the first class, the mean is mu. The second class, the mean is negative mu. And then we want to see whether we can find out a vector W. So on the first, when this data matrix applied to beta, it will becomes 1, and the x2 times beta will be negative, whether it would happen. Okay, so the answer, this would of course depends on the SNR, basically the mean, the strength of the signal, and also the strength of the noise, and also the data dimension n. Here, a simple intuition here is because if sigma is 0, which means it's actually a Gaussian mixture model, but the noise is completely gone, then we can always find out a vector so that the first class would map to one vector, thus this would map to 0. It's always possible because of linear equation. Then if the noise gets larger and larger, then possibly this won't happen again, because the model have to fit the noise, and besides the signal part. And we're able to derive a sufficient condition in the following way, that suppose D is greater than N, and actually D can be arbitrarily larger than N, so which means the dimension needs to be at least bigger than the data size of a single class. And then if the signal to noise ratio, the norm of mu divided by sigma, is greater than this 1 over epsilon, epsilon could be a constant, but it depends on the probability, times square root of D log n divided by D times D minus n, then the neuron collapse would occur, which means you can find out a vector so that the mapping of the first class would be 1, the rest of them will be negative. So which means that we can find out a W so that it will achieve the feature vector becomes a one hot vector. Okay, so here you can see that if D is moderately larger than N, actually we need to make sure that the SNR is sufficiently large. But if the D is sufficiently large, then this the SNR could be basically greater than log n factor. But of course, if D is greater than K times N, with probability 1, we can always make the collapse happen, which means we can find out W1, W2, so that the feature will becomes one hot vector. Okay, so we will present this, post this work in about maybe 2 to 3 weeks, and hopefully we can get some feedback from you. Okay, so let me just conclude my today's talk. So basically, the theory would be we study the neuron collapse happens for the imbalanced data set on the cross-entropy loss function. And in particular, we show that the exact threshold for the minority collapse, which means that if the unbalanced ratio R is greater than certain exact number, both the theory and the experiment show that the prediction on the minority group would becomes a single vector. So we cannot distinguish the prediction in the minority groups. And also we're able to do some work for which beyond the unconstrained feature model by extending this to 2-layer neural network with particular type of statistical model, and show that if the SNR for, let's say, for like a Gaussian mixture model, if the SNR is large enough, and then the neuron collapse also would happen. Okay, so thanks for listening, and I would happy to have questions. And sorry for the noise of the construction here. But okay, so that's all my talk.
Yeah, we heard nothing about construction. Okay, All right.
Okay, it's quite annoying from my side.